Hello, thanks for everyone for coming. So 2 years ago in February 2019, the modeling sub-team had a meeting on SIMIP, the Sea-Ice Model Intercomparison Project. The experiment has been conducted in 2019 and 2020, and there are some copies of IPCC chapters being circulated around. And so we wanted to touch base on some recent results from SIMIP and go over that. I guess I should say a few words about IARPIC. So IARPIC is the Interagency Research Policy Consortium for the United States. So it's a method for us to exchange information and to advise the agencies about research that's going on. So we have this IARPIC collaboration site to exchange that information. And of course, we welcome our international collaborators as well. So we've asked everyone to introduce themselves in the chat. And I guess now we can just go on to, we'll have an introduction from the SIMIP co-chair, Alexandra Jahn, from Professor Jahn is from the University of Colorado at Boulder.
Okay, thanks, Richard. And I hope you can all see the screen. So yeah, it's been almost 2 years since we had an update from the Sea-Ice Model Intercomparison Project, SIMIP, for SIMIP 6. And back then we had just started kind of to see some first results or some first runs become available. So now 2 years later, there's actually a lot of runs that are available and that have been analyzed. And so if you're not familiar with the Sea-Ice Model Intercomparison Project, I just wanted to give a very quick introduction. So the aim of SIMIP is to better understand the role of sea ice for the changing climate. And it's a endorsed MIP for SIMIP 6 that's co-chaired by Dirk Knotts and me. And it's a diagnostic MIP, so we didn't propose any specific experiments, but just worked on refining a variable request to do more advanced analysis to be able to look at sea ice process understanding in the SIMIP 6 simulations that we're going ahead anyways. And we have a website that's shown here where we kind of update as things are happening throughout time. We had the third Sea-Ice SIMIP workshop in August 2019. That was a half-day workshop before the IGS Sea-Ice meeting in Winnipeg. And we had planned to maybe have a workshop this year, but at this point we haven't set anything, kind of just waiting to see how the pandemic ends and when we have capacity to do that again. The big 2020 accomplishment was the publication of a SIMIP community paper on Arctic sea ice and SIMIP 6. And so that came out in early 2020 in GRL and was really a community effort to describe the simulation. And so I just wanted to show a couple of quick slides from that. So the main takeaway here is that the historical SIMIP 6 Arctic sea ice area spread and mean quantities are not much different from SIMIP 6. So nothing fundamentally has changed in the sea ice simulations. I was looking at March and September, the sea ice area over a decade at the beginning of the observational period, satellite observational period, and showing in SIMIP 6, 5, and 3. And we can see we remain to see a really large spread in the models. And the mean didn't change significantly either in September or in March. So not much different was the main conclusion from this analysis. What has changed a little bit was the Arctic sea ice sensitivity, both in terms of sensitivity to CO2 and in terms of sensitivity to global mean temperature. So here I just pulled out the one for the sensitivity to CO2. And so here we do see some change and also change over time going back to SIMIP 3. So towards in the right direction. So that's good. It's a promising development, but partially that is also due to the fact that now the spread is even larger and there's more models that have a higher sensitivity than what was previously seen in SIMIP 5. kind of changing the mean in that direction. And in this overview paper, we kind of just documented that. We didn't have space or capacity at that time to look at whether this really reflects an improvement of the model physics or primarily arises from the change in the historical forcing in SIMIP 6 to SIMIP 5. And so that's an active area of research, including in my group, and I know in many others as well, to try and understand why we're actually seeing this change in the sensitivity, and also kind of understanding that on a model by model basis. And then looking into the future, one of the SeaIce SIMIP 2020 main results was that the timing, or the first IceFree Arctic, actually is not scenario dependent. This is showing a figure that Dirk made afterwards based on the results from the SIMIP paper, looking at the fraction of the SIMIP 6 models that show an IceFree Arctic over time. We can see that under all, I didn't put in, I think, the key but for these scenarios, but this is RCP 8.5, 4.5, and 2.6, and we see that it's pretty much the same. We don't see a scenario impact, and it's likely that there will be at least one IceFree Arctic in September before 2050, and then the reoccurrence depends on the scenario, but just happening for the first time, it is not scenario dependent. So that was kind of just a quick overview of the findings from that paper. And so there's many studies of SeaIce and SIMIP 6 ongoing, several under review, and a couple already published. And so we're currently collecting these papers that are SeaIce MIP related, self-identified if you were inspired by SIMIP or used the output or part of one of the focus groups that we tried to organize.
Oops, did we lose Alex?
It does.
That's what it looks like.
Yeah.
She's still showing up in the participants list.
Okay. Well, I think, fortunately, I think she was towards the end of her presentation. I think at this point, we should probably go on to our first speaker, if that's all right. And our first speaker is Dr. Abigail Smith. Dr. Smith received her PhD last month. Alex Jahn was her advisor at the University of Colorado in Boulder. And she's now at NCAR, the Research Applications Laboratory. And she'll be talking about seasonal transition dates. Abby?
Great, thanks. Can you hear me okay?
Yes,
Yes.
And we can see your slides.
Awesome. Okay, yeah, thank you for the introduction, and thanks to the organizers and everyone who's tuned in this afternoon. I am going to be talking about seasonal transition dates in Arctic sea ice. And sorry, I'm just going to change my laser pointer for a second to the arrow. There we go. Great. Yeah, so I'm going to be talking about seasonal sea ice transition dates in the Arctic and how they can reveal biases in sea ice simulations. And I did this work with Alex Jahn and Nguyen Wang while I was at the University of Colorado. And now, as Richard said, I am at the National Center for Atmospheric Research in Boulder. So I'll start by discussing an important aspect of Arctic sea ice that you're probably familiar with, which is that it has a really dramatic annual cycle. And the video that I'm showing starts in March of 2020, March being the time of year where we typically see the maximum sea ice coverage in the Arctic each year. And then we can tell based on this video how dramatically the ice cover changes throughout the summer until we reach that sea ice minimum that typically occurs in September. And the 2020 sea ice minimum in September was the second lowest on record. So you can see how dramatic that looks compared to that 1981 to 2010 average minimum in the yellow line. So what we've done is break down this really dramatic change that happens every year into a set of distinct dates. starting with the melt onset in the spring, which we define in the models based off of a change in the surface temperature. We then define opening dates, which is when the ice concentration at a given grid cell passes below 80%, and then breakup dates when it passes below 15%. We also have a set of fall transition dates, including freeze onset, which in the models we define based on surface temperature, and then freeze up, which we define based on the 15% ice concentration threshold, and closing is that 80% ice concentration threshold. So we have these sets of discrete dates that we can think about these seasonal transitions. And we also can use the time that elapses between them, including the open water period, which we typically think about as the time between breakup and freeze up. So using that 15% ice concentration threshold. So to give a little motivation for why we're interested in model projections of seasonal transitions and to draw on the SIMIP concepts here, I'll start by saying that Alex showed some really relevant slides that demonstrated the large sea ice area spread in the models. So we see this large spread between the models in SIMIP 3, SIMIP 5, and now SIMIP 6. And so the differences between the models is on the order of millions of square kilometers, and the causes of that spread are not well known. There are also large projected changes and uncertainties in the sea ice seasonality itself. So the figure I'm showing here is from SIMIP 5 models. We have the median breakup and freeze up dates as this thick line, and we also have the interquartile spread between the models as the shading. And we see that in the 20th century, the length of the open water period, the time between these dates, is about 2 to 3 months, but is projected to increase by 2100 to about 6 months in terms of the Pan-Arctic median. We also see from this figure that the spread between the models is quite large and is also projected to increase over time. So the objective of this work is to use a range of data products to investigate when and where thermodynamic processes may relate to sea ice biases in climate models to help contextualize some of these questions about the spread and projected changes. So a few key results that I'll discuss are that models capture the observed asymmetry in seasonal transitions. We also see that seasonal transition dates are related to other characteristics of the ice, such as the area and thickness, and that biases in the seasonal transition dates can compensate for other unrealistic aspects of the simulated sea ice. And this talk is based off of a paper of the same name that was published in the Cryosphere last year. So just to give you a little background on the tools that we are using here, we're using global climate models and satellite data in their overlapping time period of 1979 to 2014. And so that means we're using the historical forcing in the models. And the first set of ensemble members we're using is from the Community Earth System Model Large Ensemble, which has 40 ensemble members with slight perturbations in the initial conditions to each member. We're also using SIMIP 6 models. At the time that we did this analysis, there were 15 SIMIP models that output the daily sea ice variables of interest to creating these metrics. And 2 of those models have more than 30 ensemble members. So with those 2 models and the large ensemble, we're able to create a few different representations of internal variability in these metrics as well. And finally, for the observational data, we're using the Arctic sea ice seasonal change and melt and freeze climate indicators. And that provides a set of satellite observed metrics similar to what I described before. So first, let's assess how well models actually simulate these seasonal sea ice transitions. And what I'm showing here is the mean melt onset date in one ensemble member of each model and the satellite data here in this first panel over 1979 to 2014. And we see that models tend to agree with satellite data on the timing of spring transitions in that they have earlier melt onset dates in the marginal ice zones and later in the central Arctic, as we would expect. There are a few exceptions to this. There are a couple models that show really late melt onset dates, and I promise to talk about them in a couple slides. But in general, as we move into opening, we see that the spring transition dates continue to look consistent between the models and the observations. Opening, as you'll remember, is when ice passes below that 80% threshold in concentration. And so you do see in some models that we start to get areas where that criteria is not met in some parts of the Arctic. And that becomes increasingly important as we go into breakup, which is that 15% threshold. And so you can see from this figure that there is substantial disagreement between the models on where that threshold is consistently crossed each year. And so when we compare between the models and the observations, we have to look at where they both tend to have breakup dates. And if we do that, then they agree well between the satellite data and the models. Fall is a little bit of a different picture. So going into freeze onset, I'll first start by saying that I mentioned earlier that we use 3 different models to create ranges of internal variability estimations in these seasonal transition dates. And for the freeze onset dates, 10 out of the 16 models actually show freeze onset dates later than observed, even when we consider that expected range of internal variability. For freeze up, there's a similar but a less widespread pattern amongst the models where 5 out of the 16 models show freeze up dates later than observed, even when considering that estimation of internal variability. The pattern seems to taper off as we get into closing dates, which tend to agree relatively well between the models and the satellite data. But you'll notice that the last 3 figures that I showed there, those fall transitions all appeared more similar to each other than the spring dates. And that's because spring ice loss takes about 1 to 2 months longer than fall ice growth. And the climate models are capturing this asymmetry well. So now that we know about how well climate models are representing these seasonal transitions, we want to draw connections between these dates and other aspects of the sea ice that we're interested in, including the sea ice area and thickness. So what I'm showing in these plots is the mean freeze onset date on the y-axis, and then the x-axis is different between the two. There's a mean summer ice area on this x-axis, and then mean March ice thickness on this one. And each of these points is 1 year in one ensemble member of each model, and the models are all color-coded up here. Satellite data is in the black triangles. And what we see is that there are clear relationships between these dates and the area and thickness, where we have lower summer ice area corresponding to models with later freeze onset dates, and models with later freeze onset dates corresponding to lower March ice thickness. These patterns continue through the spring, but are weaker than the relationships that we see in the fall. And so I'm showing melt onset date on the left axis now here. And we see that models with lower March ice thickness tend to have earlier melt onset, and in turn, models with earlier melt onset have lower summer ice area. So we have this year-round connection of seasonality and area and thickness. We also see that we get a better visual representation of the spread between the models than we did with the spatial plots. And so we can see that there are large differences between the models in terms of their representations of these melt and freeze onset dates. And we do have some that fall outside of what we would say are the expected ranges of internal variability that we get from these kind of clouds that have more ensemble members. So these differences between the models are likely due to actual differences versus internal variability alone. And I mentioned before that there's a couple models that have particularly late melt onset dates that I'll talk about next. So we do see this green cloud here shows a couple models with really late mean melt onset dates over this time period. And we also see that they have unrealistically thin ice in March. However, counterintuitively, those models do have realistic summer ice area where it falls between this model spread and tends to agree well with those observations that are the triangles. So this leads us to believe that the late melt onset dates in the models are actually retaining thin ice that would otherwise disappear over the summer, and in turn producing realistic summer ice coverage for the wrong reasons. So this shows us how biases and seasonal transition dates can actually compensate for and obscure other unrealistic aspects of the simulated sea ice. So I'll just wrap up by hitting these key points again, in that models capture the observed asymmetry in seasonal transitions, where we have the spring ice loss taking 1 to 2 months longer than the fall ice growth. Seasonal transitions also affect sea ice area and thickness year round, so we can get a more process understanding by using these dates. And finally, biases in seasonal transition dates can compensate for other unrealistic aspects of the simulated sea ice, at times leading to September ice areas in agreement with observations for the wrong reasons, which kind of speaks to the importance of using more process-based metrics to evaluate sea ice and climate models versus just using September sea ice area alone. So hopefully I've convinced you that these sorts of dates can help us understand Arctic sea ice processes and climate models, and happy to take any questions and looking forward to the discussion.
Thanks very much, Abby. Let's just go to questions. If you'd like to unmute and then ask a question, please go ahead. Ed, I noticed you had Ed Blockley, I noticed you had a question in the chat. Would you care to unmute and ask your question?
It's not really a question, it's just a comment about the CNRM model problems. I know that they've been fixing them, but they have had they had some really unrealistic melt ponds as well in some of the developments that they've been doing with that model. So they had to fix some aspects of the surface scheme. So maybe they'll be updating those on the SGF at some point. I'm not sure.
That's interesting. Thanks, Ed.
So just to follow up on that, Abby, in your I took a look at your paper over the last few days. In the supplementary, you showed the precipitation for the Central Arctic, and it shows that the CNRM has unusual amount of precipitation in the Central Arctic, and that kind of inhibits the ice growth. From your plots, it seems that the CNRM is kind of the outlier. Does that mean the other models are behaving better in terms of precipitation with regards to sea ice?
So I think that it's a little bit difficult to say in general if they're doing better in terms of so what I looked at was the snow thickness on top of the ice, because based off what I had read about the CNRM models, there was this idea that maybe there was too much snow on top of the ice and that it was over insulating the sea ice so that the thickness below couldn't reach a realistic thickness. And so I think that feedback was where the CNRM models may be having trouble. And I think maybe there could be models in here that have realistic snow, but perhaps that feedback isn't quite realistic. It kind of depends on both factors of whether you have the right amount of snow on top of the sea ice, but also if your sea ice is sensitive enough to that. And so I think it's a little bit difficult to say in general if the models other than that are doing well.
So compared to the other models, the CESM also seemed to have a large amount of snow over towards Greenland, but that didn't seem to have the same impact on the growth and melt seasons. That's just because it's in the location where the perennial ice is, then I would guess then. Yeah.
And what I'm showing here is the Pan-Arctic means. And so we're not, quite getting the regional differences in the impact that would make. But it would be interesting to see like similar figures for this divided up by region.
Hi, Abby. This is Hyuntang. Very nice work. I wonder when you do the calculate the Arctic mean onset or time, or how do you consider the latitudinal dependence?
Yep, so we don't normalize it for the latitude, and it's a tricky question to determine how we should define the melt onset. because the way it's actually defined in satellite observations is based off of a change in the surface brightness temperature, which isn't a quantity that's simulated in climate models, though myself and others are working on satellite simulators for this purpose. So right now, it is currently defined based on the surface temperature passing a given threshold, and that's consistent everywhere in the Arctic, and it's not dependent on the latitude.
Okay, right. Thank you.
Yeah.
Anyone else? All right, let's go on to the second talk then. The second talk is by Dr. Ed Blockley. He is the lead for the Polar Climate Group at the UK Met Office Hadley Centre, located in Exeter, where it is, I guess, 8:30 p.m. And we're very happy to have Ed here with us today. And he'll be talking about an analysis of the Arctic sea ice mass budget.
Hello, everyone. Can you see my slide okay?
You can see your slides and we can hear you well. Thanks.
Fantastic. So yes, I'm going to talk about the SIMIP mass budget intercomparison, and this is this slide just shows the paper that's been recently accepted into the cryosphere. Lots of names here from around the world, including at least one that I've seen here today, Dave Bailey. And this will soon be, it's just in press at the moment, so it should soon be available. And it's led by Anne Keane in my group. So to motivate the study of mass budgets, this plot on the right I've adapted from Francois Massonet's paper, just to show, that sea ice is declining quite rapidly over the last 4 decades, as we all know. But the model spread there is quite big, as Alex mentioned in her talk, and this is actually SIMIP 5, but the same, of course, is true for SIMIP 6. Some of the key questions that I have looking at a figure like that is, what's driving the differences between those models? And for example, is the pink line there, is the sea ice very high there because of some aspect of the sea ice model responding differently to climate warming, or is it that the sea ice model is being forced with very different ocean and atmospheric states, or maybe initial conditions? And to really understand these kind of questions, we need to go beyond the sort of traditional integrated metrics of extent and area. Well, area and volume, extent should be thrown away. And our plan here is to consider to look more at the effect, to look at the causes rather than just the effects, which are, again, area. So we're really, really lucky that for SIMIP 6 we have all these fantastic SIMIP diagnostics. Alex mentioned earlier, there's a lot of diagnostics there, and in particular from our interests, there's all of the components of the sea ice mass budget as mass fluxes. So we're now in a position that we can compare the processes of ice growth and loss in the climate models in a much more detailed way than we've been able to do previously. So very briefly, I'm just going to outline what the sea ice mass budget. This, of course, is a big chunk of sea ice sat between the ocean and the atmosphere. That's what it all looks like. The ice grows by basal growth, or it grows by fresh ice in open water. There's also some snow ice formation, which is a very minor aspect, which is why I've used little dashed lines there. And then when the sun comes out, the ice melts from above. It also melts from below and from the side because of the ocean. And then we have evaporation and sublimation, the very small terms. So the big terms here are the ones with the solid lines and the bold type font. But we're looking at an Arctic domain. So then we also have dynamical ice loss or gain. So it's generally lost, but there is a very small amount of ice convects into this domain. So this here on the right is the domain that we're looking at, and this on the left are all the processes that we're interested in. And what we've done is we've led this international mass budget intercomparison activity that we started in the EU Applicate project. We originally had plans with NCAR to just do a comparison with CSM, but we've extended this through SIMIP. And what we've done is we provided processing tools, scripts and masks to all the modeling centers, and they generated their own data and sent them in to us. Scripts and things are still available if people are interested to use this kind of stuff. And we've concentrated on sea ice mass and area over the period 1960 until the end of the scenario runs in 2100. And we're using mass because the sea ice MIP diagnostics are mass fluxes. Of course, the model prognostic is volume, but it's just multiplied by a number in our constant density models. So we've received data from 15 different SIMIP 6 models and from 9 different modeling centers. But as well as the mass budget, we asked them to send in area and mass as well so that we can do quick comparisons. And so here is just looking at what the area and mass look like in these models. And looking up in the top right, these dashed lines are September area. And this is basically the same as the Massenet plot in SIMIP 5. Lots of spread across September area. The same is true for the winter, and you can see that actually a lot of the models are starting to drop off a cliff a bit in winter, and the time at which they do that is all very different. Although I like to think that the decline looks quite similar in all the models, but that could just be wishful thinking. There's also quite a big spread here in mass, although as you get into the later periods, to 2020 onwards, the mass decline does look quite similar, the trend in each of the models, but again, that could just be wishful thinking. So there's quite a lot of spread between the simulated area and mass in these models, and we want to have a little look at what's driving that. So first we concentrate on this 1960 to 89 period. This is our reference period, and that period on the top right is the seasonal cycle of the mass budget, and you can see that it's dominated by melting in the summer here, which is mainly top melting here in blue and basal melting in green. And then during the winter, there's net growth, which is mostly driven from congelation growth of ice at the bottom of existing ice. There's also some open water formation there, which is this sort of purple color, frazzle growth. But the models pretty much all agree pretty well. So here that these are plus or minus 1 standard deviation across the models. And the models agree pretty well. They all agree that it's net loss between May and September and net growth between October and April. They also agree pretty much that basal growth is dominating the growth of ice, and that basal melting is more important than top melting, although there's a few differences there. And all the models have net dynamical ice loss, which is, of course, is mostly lost through the Fram Strait into the North Atlantic. But the agreement between the dynamics is a little bit more sketchy. I'll show in a minute. So please don't try and absorb all of these these plots. I put this up just to show that how similar. This is all 15 models that have gone into making that last model, the annual means, and they're all quite similar, i.e. broadly agreeing that there's lots of basal growth and lots of basal melt. Those other smaller terms are not included here because they're all very small. So as I say, the annual budgets broadly agree across the models, and seasonally as well. There's quite a strong agreement between them as far as the timing of when processes are important. But the absolute values can be quite different, the magnitudes, and sometimes the relative magnitudes. So you can see here that there's a lot more frazzle growth in this model and this model, and a lot more basal growth in this model and this model, and often there's a balance between the two. The one that's the most different is the dynamics. So I just have a zoom in on that here. It's a bit crazy, really, the dynamical loss, but most of the models agree that extent is his export is negative all year, and its maximum in March and minimum around August. It looks a bit like this very technical seasonal cycle I added in PowerPoint this morning. However, some of the models look really different from that. So there's quite a difference here. I don't have time to go through this, but in the paper, we also had a look at how certain aspects of the model physics might impact these differences, particularly in the reference period. And there were some aspects of the differences we could attribute to certain models. For example, in black here, the UK models generally have a lot lower basal melt and relatively higher top melt. And these models here that are based on CSM, they have very, very similar basal melting and basal growth and top melting, but for some reason very different frazzle formation and dynamical losses. So we go into a bit more detail about these in the paper, but I don't have time to go through those at the moment. So then we looked a bit about how the budget changes in the future, and these are decadal mean evolution of the budgets. The top right plot is not very interesting. It just tells you that as the sea ice is declining, you know, all of the processes, all of these different processes are declining as well. But if you look in the middle plot, these are anomalies relative to our reference period. You can see that initially around year 2000 or so, the ice is actually increasing in mass because of decreased export and relatively more increased basal growth and being decayed by more melting. But this changes after about 2040 and the actually sign changes these thermodynamical processes. So then ice loss is being driven by lack of basal growth rather than more ice melting. And then if we look at anomalies per unit area, which is the bottom right plot, you can see that for example, basal melting just increases, gets even more and more important. So as you get to about here, there's not much ice left in the summer when there's any sun, and so top melting just dies off because all the ice exists in the dark. It's a bit of a sad state of affairs for it. And we've also looked at the seasonality of the budget changes. No surprise to learn. So actually the top right, which said the solid lines are the mean budgets for the reference period, the faint ones, and these new solid lines are 2040 to 2049. So when a lot of these models are actually ice free. And so we get a lot more melt earlier in the season. This bottom plot is showing the anomaly, the seasonal cycle anomaly. We're getting a lot more net melting here, particularly in June, top and basal melting, and then less later in the season because there's less ice around. And likewise, we get a lot less growth of ice in the autumn, which I think is mainly because the freeze up is later and the ocean is warmer, and then you get a lot more growth actually later in the winter because of the ice being thinner. So that's a thickness growth feedback. But the timing of the net melting and growing doesn't change. The models are still saying it's between April and May that we go from net growth to melting, and between September and October that we go back the other way. And that might be because we're looking at base and mean, and we're looking at monthly mean, so we might not see the granularity of any changes in sort of freeze up melt dates. Now this is a crazy picture. I'm not expecting anyone to look at this and understand it, but the point is there's still quite a lot of spread between all the different budget changes. If you just look at them from a temporal point of view, it doesn't look any different than when we had looking at the actual area and mass. But if we change this plot so that we're plotting mass budget changes in relation to the ice state itself, then all the models start to exhibit some quite common behaviors. For example, here the mass loss in relation to the actual mass of ice in the Arctic is relatively stable until we get to a point here where the ice just gives up and says, I can't live anymore. There's not enough of my kind. And so it just, all the models actually drop off at a very similar rate. And likewise, we have this situation where for ice area in the present day, which is on the right here, we're getting a lot more melting. But the basal growth is very similar. But then as the ice declines, actually the melting is no longer what's removing the ice, it's the lack of basal growth. And all the models are showing these behaviors. And and even the dynamics, which is a bit crazy. Generally, we say as the ice mass decreases, then the dynamical export is always changing in a fairly linear way. So this suggests to us that the mass budgets of all these models are responding in a broadly consistent way to the warming of the climate. So in summary, we've done this intercomparison. It was great. There was a lot of models and modeling centers signed up, which was fantastic. And for this reference period, we find firstly that the budgets are quite similar between the models, both in terms of the dominant processes and the timing in the seasonal cycle of when these processes are important. There are some sort of granularity differences between the models, and some of these can be attributed to differences in the physical schemes and parameter settings in the models themselves, but not all of them. As the ice declines, the timing of the top and the basal melting shifts, largely as one would expect, but we don't see any difference in the timing of the length of the melting and growing season, if you like. And then finally, this last point I made, the models are quite different, but if you look at them in relation to the ice state, then they do exhibit quite common behaviors. And this suggests that the models are broadly responding in a fairly consistent way. We're not sure how happy we are about this. I mean, these similarities between the reference periods, the mass budgets between the models, and in the response to warming are quite good, and they do give us some confidence in the physical realism of the model. But we're just concerned a bit they could also be indicative of low model diversity across the ensemble, particularly as a lot of the models are structurally quite similar, being all based on the sort of Ajax continuum style model and they've all got VP style rheologies. So we suggest that maybe further investigation using models from outside of SIMIP might help to shed some light on that, for example, using other rheologies like the EAP or the MEB, or maybe some different model simulations that are not Ajax continuum models. So finally, just to say this paper is in press at the moment. There's the obligatory 4,000 bullet point list of you forgot to define this acronym, or this paper needs a better citation that Anne is currently working through, and it will soon be available online. So yes, that's the end. Are there any questions?
Thanks very much, Ed. Let me just see if there are any immediate questions from those online. I see Hyuntang has raised his hand. Hyun, can you unmute yourself and ask a question?
You're unmuted, but we can't hear you. Could you maybe write your question in the chat box and then we can read it? Oh, perfect.
In the meantime, Ed, is it worth doing this type of analysis for smaller regions of the Arctic to understand the differences for the various regions, or would that start to expose the large biases and the sea ice extent among the different models?
Yeah, that's a good question. We've considered it, and it would probably be more useful to look at that in the reference period, you know, when all the models are fairly similar. But as you say, as the ice changes through the 21st century, then it's quite different. So we have to put all of these budgetary changes into context with the amount of ice that's there. It's a lot easier just to do it in the basin scale, but it's much less useful. I guess it would be nice to have more of a regional analysis. So this is something that we're thinking about.
So Hyuntang has written, what are the main, oops.
Oh, I think I can move my stuff now. Can you hear me?
I can hear you. Yeah.
Hello.
Yeah. I just have a very naive question. I wonder, what are the main drivers for top versus basal melting? Can I say the top melting mainly driven by atmospheric processes, while the basal melting can be mainly driven by ocean processes?
Yeah, I mean, that's the bottom line, although a lot of the ocean melting does come indirectly from the atmosphere as well. So a lot of it is localized warming from the atmosphere, but some of it has come in from the Arctic. I guess it depends where you are, particularly if you're in the Barents Sea, then there's quite a lot that's come in from the Arctic. But one of the reasons we've looked at the central Arctic rather than doing the marginal seas is, there's a lot less ice, because if you look at the marginal seas, you have ice that goes out and then it mostly melts via ocean processes. So we've just said that's dynamically lost already.
Okay, thank you.
And as Abby suggested, that some of the basal melting could be affected by the amount of precipitation on top of the ice. And I was also going to ask about the differences among the models with the frazzle ice. Does that suggest that there are significant differences in the mixed layer among all these models?
Yeah, so I didn't talk about those too much. So there are some issues. One is basal melting versus lateral melting, which generally I lump together and call ocean melting, because the partitioning is the choice of the modeler. And the same is true for frazzle formation versus congelation basal growth. So the GFDL model has got no frazzle formation virtually, but because what they do is when ice forms, it's an infinitesimally thin layer on the surface, and then any further growth is considered basal growth. Whereas in the limb-based models, if there's enough cold and to form ice in the ocean, then it goes in at 10 centimeter thickness, and that is counted as frazzle formation. And so it kind of the choice of your model, how much your minimum thickness of ice is. So we haven't looked too much at those.
Okay. So Wisla has asked a question in the chat here. He says, you mentioned sea ice parameters are part of the reasons for differences. Could you comment on the role of atmosphere and ocean? I guess that's a similar question to what Hyun was asking. Yeah,
I mean, they're both important. I think more so. So what we show at the end is that the models are largely responding in the same way to the warming of the surrounding climate. So I think the warming of the atmosphere, the climate sensitivity of the model is much a bigger driver of changes in the sea ice than any aspect of the sea ice model is. But we tried to split these models up to look at any particular models and particular aspects of the atmosphere, ocean, but we don't have a big enough subset to do that, or looking at resolution or anything like that.
Wisla, do you have a follow-up question? Do you want to unmute?
Well, basically, what I got from Ed's comment is like, okay, the sea ice parameterizations might be part of it, but if you have cloud problems and radiative budget at the surface, that would be the primary driver, as you just confirmed, and maybe including in the warming of the ocean due to the changes in radiation budget at the surface as well, affecting your basal melt. So my point is just basically the sea ice could be as good or as bad as any other models, but if you have a big differences in energy budget at the surface, that will be primary driver for most of the spread in the models.
So we have a sort of an extra bit that I didn't present today because I didn't have time, but we did some side simulations in this paper with a forced model that the guys at David Schroeder did at CPON, where they took their forced model and they show that the budgets can be quite similar to our couple model that it's based upon. And then they've done some tests where they've changed the forcing, atmospheric forcing, and you can change the budgets completely that way, or they've completely changed the physics of the model using EAP, rheology, and various other things, and show that actually that also changes the budget. So the Sea-Ice model is heavily driven by its own physics, but also by the forcing data sets either side. We didn't do any ocean sensitivity per se, but I imagine it would follow the atmospheric forcing quite closely.
So Caitlin Florentine has a question in the chat. For Dr. Smith, what ice thickness data are used to define initial conditions for the sea ice models? So these are SIMIP 6 models. So they're kind of, spun up and they have their own sea ice thickness. Abby, do you want to say anything else to that?
No, that's about the extent of my understanding, and everyone's approach will be different, but I think
you can see on my slides actually the spread in ice mass there is the same as the spread in ice thickness. So there's a huge ice concentration extent differences are quite large, but the thickness volume ones are much larger because they're relatively unconstrained in climate model spin ups, I would say.
Yeah.
Can I add to that too?
Yes.
Dave Bailey here. So what we typically do for these CMIP sort of scenarios is we all run 1850 pre-industrial control runs for thousands of years where we get a sort of spun up initial state. And then we often run multiple 20th century members where we initialize, we pick different points from that long pre-industrial control run. So in terms of the initial conditions for the thickness, it's taken from this pre-industrial 1850 state, essentially.
Does the UK Met Office do something very similar to that, or is it different?
Yeah, so we run our spin up 1850 pre-industrial control, as most people do, and then when we do our historical members that become the scenario members, we've chosen, we don't have very many ensemble members, so we choose them particularly so that they span they try and span the state of variability. So we look at things like AMV and PDO and make sure that we have a little cross section of those and make sure we span the available variability. But yeah, similar. I noticed a question from Caitlin in the chat, and the answers that for my bit is she asked about future scenarios. We only looked at the SSP 5 8.5 scenario because we were interested in big signal to start with and see how that impacts the mass budgets. So I don't know whether the timing would be different.
Sorry, Abby showed the other scenarios, and she suggested that the length of the melt season did not vary among the scenarios. Is that right, Abby?
Oh, no, I didn't actually show any future projections here. Alex showed something about the first ice-free conditions not being dependent on the scenarios.
Oh, okay.
Yeah.
One thing that's happened for SIMIP 6 is a lot of the models don't show any difference in ice-free date across the scenarios, because the scenarios, they don't diverge in temperature until after the 2040s, and a lot of those models are ice-free in September by then. Our models mostly. So we don't see any difference in the scenarios, but we do in winter. So we start to see almost ice-free winters towards the end of 2080s in the high emission scenarios, but it actually it's stable in the 1.9 scenario.
Okay. So 2 years ago, Mike Witten was one of the speakers for our introduction to SIMIP, and he asked the question, can we assess sea ice model quality from the sea ice and Arctic, the sea ice Arctic trends and projections? So can we assess the model quality? It just seemed from the results that I've seen here that there is a lot of similarity. Well, there's certainly a large spread, but once there's a bias correction done, there seems to be some similarities in the characteristic and the behavior of these models. Is that fair to say? Ed?
Well, that certainly is one of the main points that we're trying to make in this paper, is that the response to warming seems to be very similar in all the models. And that's not surprising given the stuff that Alex showed at the beginning from the SIMIP paper, that they're quite similar in their response to global warming, the sensitivity of the models. There are some slight differences in the physics. So something I've been looking at more recently is looking at relationships between these past mass budgets and future decline of ice. And it looks like models that have the most elevated mass budget cycle in the past lose their ice sooner in the future.
And so this is also the motivation for looking at different ice rheologies or different types of models to see whether that creates more heterogeneity in the response then.
And there's a lot more diversity across the atmosphere and the ocean models used. The Sea-Ice models are quite similar in that they're pretty much all using EVP. They're all a sort of dynamic thermodynamic model. There's some differences in the physics, like different thermodynamic schemes that we have shown they can impact things a certain way, but structurally they're very similar. In fact, structurally very similar to how they were in the 1970s and 80s.
So I think the Met Office is in a bit of a unique position. You guys were part of you can correct me on this, you were part of the Sea-Ice Consortium at one point, and for SIMIP 6 you used the LIM 3 model.
No. All of our models for SIMIP 6 are based on size 5.1.2.
Okay.
We have a slightly different version. So we're in the paper, we split things up according to model and various other different processes. So we look at whether those factors influence the model. But no, our model and the Australian and New Zealand models and South Korean models that are based on ours, they're all using size 5.1.2.
Okay.
But it is quite different in its setup to the CSM model. They're using different melt bonds, different thermodynamics, and quite a few other differences as well.
I see. Okay. It's getting towards 4 o'clock. Are there any other questions from the audience? And I don't see any in the chat. I'd certainly like to thank the speakers. Alex, I'm sorry you had some internet difficulties, but thanks for that introduction, and thanks to the 2 speakers for presenting. I think this was a pretty good meeting. This is a very good meeting, and thanks to all the participants who logged in to listen. I think this was very good. Thanks very much.
Thank
Richard, maybe Anne still has some announcements to make.
Okay, go ahead.
Did you have something specific in mind?
I thought this was that's what you indicated in your email, that you wanted some time to.
Well, I can announce it. So it looks like with the new plan rolling out at the end of the year, the sub-teams will be elevated to collaboration teams. So congrats to all the sub-teams. I'll be transitioning out because my fellowship is coming to an end. I will stay on with NOAA and still be in the background helping the new fellow on board to support the current teams in IARCBIC. Is there anything else that I left out?
No, we just want to thank you a lot, and for all your help that you have given us in the past year in keeping us organized and keeping us on schedule and things like that. We really appreciated that, how much you were engaged with our team. So thank you very much for that.
Thank you.
Thanks very much, Anne. Speaking of disorganization, I'm not sure what our next monthly meeting will be about. I think, Wilbert, was that going to be the modeling center lead?